All right, friends and neighbors, welcome back to another networking video. This is going to be Chapter 27 on the CCNA. This video is probably going to be one of the weirder ones that I've done, only because I'm recording this on Amtrak's the Southwest Chief. And so hopefully the audio is okay and the lighting's okay, but the audio is more important clearly. But here we go, Chapter 27, implementing IPv6 addressing on routers. Now, as always in this video, we'll do the key topics, and our exam section is network fundamentals, configuring and verifying the IP addressing on a router interface, and then the prefix. We'll do a couple of router commands this time out, and then describe IPv6 address types. We've done a couple so far, and we're going to fill in some blanks, especially the link local and multicast and some specials. And we'll finish off with the "Do I know this already?" questions. So our key topics, the need for dual stacks. Now what this is referring to is, are you going to run IPv4 and IPv6 at the same time? Creating rules for IPv6 addresses using what's called EUI64. So we'll do an example of how to convert those addresses. Then we'll talk about how to turn on IPv6 on an interface, how to get routing working. We'll talk a lot about the link local addresses and what some of the scope details are. And then we're going to talk a lot about some crazy addresses. One of them is the solicited node multicast address, and then other special IPv6 addresses. Now, what helps me remember a lot of these crazy addresses is that IPv4 has the same sorts of addresses, right? We know that we've got an IPv4 multicast, we've got unspecified, we've got loopback, we've got the on-link addresses, right? Our globally unique addresses. So IPv6 is just trying to do the same thing. So when we're doing IPv6 on routers, we're going to pick a set of protocols. Now this is true of your hosts, printers, gaming consoles. It doesn't really matter. You're selecting a protocol stack. And what that means is that if you're doing IPv4, you've got an IPv4 protocol stack. And with that comes TCP, IP, and the UDP IP, a set of protocols. Now the differences are that when you do IPv6, there are other protocols and we get rid of some. So for example, we get rid of the address resolution protocol. But if you want to do both at the same time, then you're going to be doing what's called dual stacking, right? Your machine has to understand both IPv4 and IPv6 addressing. Now it turns out on the most hosts, IPv6 is enabled by default. So even though you think IPv4 addressing and IPv4 networking, IPv6 is still there. We sometimes turn off IPv6 if we want to optimize what our interfaces are doing, but it's on by default in many cases. That's not true with a router. So when we give a router an address, we usually give it a static IP address, right? We can do DHCP, but we usually do static addressing. And when we do static addressing, as we did last time, you can configure the full 128-bit addressing with the 64-bit mask. You can also say, well, I'm going to give you the prefix, and then I'll let the router derive the second 64 bits. Now we know we can do some crazy things with an interface. With a standard router, it's already configured for IPv4 routing. All you have to do is give it an IP address, and it builds its routing table, and so on. We also know that if I want to take a router and turn it into a switch, I can do that. I can say I want to make this a switch port, or I can take a switched port and turn on IP routing on that box. Now when we want to turn on IPv6, as again we saw last time, we have to do IPv6 unicast routing and then go into the interfaces and do those static IP addresses. Now the first one that I've got here, we saw this manual configuration that we did before, right? 2001 DB8 1111 :1/64. And that is the shorthand, right? The abbreviated version. We can also expand the whole doggone thing and write out the whole address. And then we can take a look at the address on the interface and we can do our verification. We'll do that. We'll remind ourselves how to do that here in a second. Now, just as an aside, a router doesn't actually need a globally unique or unique local address at all. You can get away with just what's called a link local address. We sometimes see this on WAN links because they're not doing applications, they're just forwarding traffic between routers. Routers use linked local addresses to get traffic from one hop to the next, and so you don't actually need a globally unique address on those interfaces. So you could just turn on IPv6 and call it a day. So let's remind ourselves quickly on what this looks like. So here is one of the topologies that we worked with last time. We've got several routers here. We're just going to take a look at router 0, and we'll remind ourselves about the configuration. We've done our manual configuration of the two interfaces. So that's the show run, but let's do a show IPv6 interface. And I'm going to point out a couple things before we get there. The first is we've got this address right here. We didn't do anything with that last time. We've got all of these addresses right here, right? Then we've got some abbreviations that are here too. We've got some stuff like this. We'll find out what those are. So every once in a while, you'll see that an address has one of these abbreviations associated with it. Now we can also do a show interface brief and get a little shorthand version of this. And again, we can see some of the addresses that are being used. And I'll point this out right now. Right here in the middle of some of these addresses, we've got this strange numbering system right here. And that is what we call an EUI64 formatted address. So that's just a reminder of what we did last time. Let's talk a little bit more about that EUI formatted address. It's called EUI64, the extended unique identifier. So what we might do on a router is give this particular command right here. So we could do the IPv6 address, but notice that here I've got the double colon, but I'm not finishing the address. I'm just adding this additional argument right here, EUI64. So in this particular method, all you're doing is telling the router what its prefix is, and then you're going to let the router figure out what its address is going to be after that. The rest of the address is automatically generated by the router, and it's based on the MAC address of that particular interface. If that interface doesn't have a MAC address, because it's something other than a standard Ethernet interface, then it'll use the MAC address of the lowest numbered interface. So here's how this works. You're going to take the MAC address and split it into two equal halves, right? So 3 bytes and 3 bytes. And then right in the middle, we're going to insert the hex characters FFFE. And then we're going to invert the 7th bit of the interface ID, which is that first half. And we're just going to flop the value on that one. Now these are where we find the universal or group bits indicating the scope, and we'll talk more about scope here in a second. But if we break out a MAC address, this is what we're talking about, where these values here indicate where the universal or group bits appear in a MAC address. Now, the chapter has a couple of conversion techniques. My personal favorites are the binary conversion. Now, I think at this point, we'll do an actual example. Now, this example appears in some other videos on the channel, but I think it's a good one, so we'll do that again here. Now, this is on a Cisco router. So we can see that the Ethernet capture shows us that the ID for the manufacturer is going to be Cisco, and then we've got the last 3 bytes, 003240. So the MAC address, we can see that right here. So here is our complete MAC address, but we can also see that in the IPv6 packet header, it's using this funny address. Now this one also happens to be a linked local address. Again, we'll talk more about that here in a second. But here is the EUI formatted part of the address, and that's what we want to examine. So the dead giveaway is that we've got an FFFE. But the question is, how did we get from this MAC address to this link local address? So what we're going to do, as I said before, is we're going to split the MAC address right in half to 2 equal parts. And then right in the middle, we're going to insert FFFE. And then if we take a look at the first octet, right, what we're after is that 7th bit. We're just going to flop whatever the value is. So here's the 7th bit, so that's going to convert to this. Now when we look at this in hexadecimal, that would be 02. So we convert that back and we put the whole thing together. We get 020F90, right? That's the first half of the MAC address with that bit flipped, FFFE, 003240, and suddenly we're at 64 bits. So we told the router maybe what its prefix would be, and this would be in the ID for or the unique ID for the interface. Now this would also be, as we saw, used with linked local addresses as well. So in the packet, if we did the full IPv6 address, it would look like that. We suppress all the zeros, and we get this combination right here. We can see that we nailed it, right? We got right to this particular value. All right, let's talk a little bit more about that link local address. Now, they're almost always going to begin with FE80. Now, RFC 4291, right, the one that describes all this addressing, talks about a mask associated with the address. So if you break out the mask and you look at the binary and you start doing what are possibilities, it turns out that the addresses could actually range to a couple of other values. But the RFC also says FE80, so all your link local addresses are going to begin with FE80. Now, for Cisco routers, certainly, we're going to do EUI64 formatting unless you specify how you want that portion of the address formatted. We talk about the EUI64 format quite a bit because you do see them. But it's worth noting that not everybody uses EUI64. It is very common to have dynamically generated linked local addresses. They're just not generated with EUI64. And that's for a security reason, because if we know that your address is going to be based on MAC addresses, then we know more about your node than we maybe ought to know. So a lot of operating systems don't use EUI64. Now, I mentioned some of the abbreviations that you might see when you're looking at your IPv6 interface addressing, right? So if you do a show IPv6 interface brief, we saw the DAD abbreviation. So there's going to be a couple that pop out, right? This one makes sense now to us. If we see an address that's EUI formatted, then we know what that comes from. If you look at an IPv6 address in the early part of the configuration, it may be tentative because it's trying to do duplicate address detection. If you're doing dynamic addresses via DHCP or SLAAC, then you might see calendared or preferred addresses associated with that. We'll talk more about those in a future video. Now at this point, what I'd like to do is show you an actual capture with a whole bunch of these addresses, and then we'll see where they all come from. Now this is a very common set of captures from a node that is started up and is trying to find its neighbors. Now the neighbor discovery protocol is something that we're going to talk about in the next video. It's part of the next chapter. But I'll introduce it here so you can see what we're talking about. First of all, I'll point out that on the all the way on the right hand side here, we've got neighbor solicitations, router advertisements, and things like that. These are messages that are part of the discovery process. And over here, we can see that almost all of these addresses are beginning with FE80. That makes them link local. If we take a look at packet 130 here, we can see that this is an EUI64 formatted address, but we can see that the one above it is not. So that is the realization that not everybody's going to be using EUI64. In addition, we've got all of these addresses that begin with FF. Now, FF is a dead giveaway that you've got multicast addressing, but I also point out that some of them are fairly long and some of them are short. Here, we've got a very, very short multicast address associated with this node. But then we've got a little bit longer one here that's also got that FF popped in there. And we're going to see that this is something called a solicited multicast address. And nodes eventually communicate with each other via these link local addresses. So link local addresses have a very important scope to us. They're used not necessarily for applications, but for communicating on your local address and between routers. Routers use them for next hops too. So there we go. This one happens to be a neighbor advertisement. So these are just examples of things that you're going to expect to see. Notice that none of these are globally unique or unique locals. So let's pull back a second and Remember that routers and servers are almost always configured statically. So you're going to have one of the methods that we were talking about today to configure those addresses. You'll either do the whole thing or you'll let the router figure it out. Now, hosts most commonly use DHCP. Now, we're very used to that in IPv4, and IPv6 is no different. Now, routers can also have a dynamic IP address. We don't do it very often, but sometimes they're done when you're connecting to an ISP or something like that. Get your IP address via DHCP, and this is the same with IPv4 and IPv6, or we can do stateless auto configuration. And we'll take a quick look at that, but that'll be also for a later video. Now we know some stuff happens as soon as we enable IPv6, right? So as soon as we do the IPv6 unicast routing and give the interface an IPv6 address, then the router starts to handle several things. Now this is much the same as we see in IPv4, right? We get the address on the interface itself. We are now going to forward packets, in this case IPv6 packets, between interfaces and figuring out the routing for those packets. We're also going to know the prefix for a particular interface, so we're going to know how to forward packets. And it's going to know that the router is now connected to an IPv6 network. And now we know that there are additional addresses that are also part of the configuration and communication. So we just talked about linked local addresses, and we also got how those are formatted. Now, linked local addresses, as we know, are for addresses or for interfaces that need an address, don't necessarily need a globally unique one, so they're not associated with application data, and they're linked local only, which means that their scope is on this link or this network. And they're automatically generated, either EUI64 or some other method. So let's take a quick look at a router, and we'll configure it fresh, and we'll see what are some of our options when we're doing our IPv6 addressing. So here we've got a brand new router. I haven't done too much to this yet, and all we're going to do is take a look at some of the configuration that we've done up to this point, and we'll add one or two things and see how that changes things. So we're going to do a show run. We can see there's our IPv6 unicast routing. In this particular case, we've just done the IPv6 address auto config. We could also enable IPv6, and our other interfaces don't have anything. So now what we're going to do is we'll say int g0/0/1, and I am going to give it a prefix. So we've got our options here. So I'm going to say IPv6 address. Well, what are our options at this point? Well, right now I'm just going to give it a prefix. So there's right, so here's DHCP and here's the auto configuration. These would be dynamic methods that we would use, but I want to use that EUI64 format at this point. So we're going to do what we've been talking about so far. If I did a 0 db8, right, I could do that, or I could just suppress the 0, 1111, and we'll leave it at that, right? So this could be an address, but I'm not quite finished yet. Here, I'm going to do EUI64. We can also see that an option here is anycast. We'll talk a little bit more about that later on. Well, now let's do our show IPv6 int command. And we can see this was the interface that we already configured, and it just has this link local address. There is no configuration for dynamic connectivity or dynamic addressing on that interface. So it pretty much is stuck with this link local, and we can see the FFFE, meaning that it's EUI64 generated. Okay, let's take a look at the next interface. Here is G001. Here's a link local address. And here is the EUI64 formatted, but take a look here. This is the global unicast, the GUA, and this one is also EUI64. Why? Because we added EUI64 to its IPv6 address configuration. So here is the subnet, and there's one of our abbreviations, right? This tells us that it is EUI64 generated. And of course, our multicast addresses. And we've got a couple of flavors here. We're going to see what this one means, what the second one means, and of course, what this longer one means as well. All right, let's figure out this whole multicast thing. A really cool thing about IPv6 is that it doesn't have any broadcast, so we don't have to think about that at all. Now, up to this point, we've got global unicast, unique local unicast, and we got a pretty good handle on link local unicast. Now, IPv6 uses multicast addressing a lot more than IPv4 does, and there are generally two ranges. The FE30/12, that's for applications, and then FF00/12, these are reserved for well-known multicast addresses. Now, a good question might be, why multicast? Well, multicast is way more efficient than broadcast. Broadcast is a lot of pollution on the network. Everybody has to listen to it, and it goes everywhere in a layer 2 topology. So it goes throughout all the switches and is only bounded by a router. Now, the nice thing about multicast is that it's only sent to nodes or only listened to by nodes that care about that particular multicast address. And switches can be configured with something like IGMP snooping to only send the multicast traffic where it needs to go. Now, before we freak out, IPv4 has the same thing in terms of the well-known multicast address, right? 224 to 239 is the range, but 224.001, 224.002. In this example here, I've got OSPF at 0.5 or .5 and .6. So IPv6 has the same versions, right? FF02::1 is all nodes. ::5::6 OSPF. So let's dive a little bit more into some particular multicast addresses and multicast scope. So I've already mentioned the neighbor discovery process, again, next chapter, but it replaces ARP, right? When you want to build a frame for somebody, you need to discover the MAC address. And so ARP is how we do it in IPv4, but it's not how we do it in IPv6. So the solicited node multicast address helps with that particular process. Now, the solicited node multicast addresses are identified by a particular pattern. So on one side, they begin just like any other multicast address, but there's a unique identifier that is tied to the node's unicast address. Now, part of this is this particular value right here, the fourth hexadecimal digit. The fourth hexadecimal digit is there to indicate scope. Now, the most common value you'll see there is a 2, and that's link local, right? So only on this particular network. But it could be larger, but very, very common values are going to be 1 and 2, especially 2. Let's take another look at that capture because there's a couple of things I want to point out. First thing we want to point out is that solicited node multicast address, which is this right here. And so in the MAC address, we saw that we've got this particular pattern. And so at layer 3, we see that particular pattern reflected in the solicited multicast address. But the other thing that I want to point out is this thing right here. It says IPv6 multicast, but at layer 2. Now, if you remember, in IPv4, if you do a unicast IP addressing, you'll use unicast max. If you do broadcast at layer 3, you're doing broadcast at layer 2. If you're doing multicast at layer 3, you're doing multicast at layer 2. And the same thing is true with IPv6, but the pattern is different. The dead giveaway that you're doing multicast with IPv6 is that the MAC address, the destination MAC address, begins with 3333. And that is ubiquitous with the multicast addressing. So in this case, we've got a source IP address that's link local, destination that's multicast, source MAC is unicast, destination is multicast. So now we can put a little bit more together. Here is an all hosts. We've got an all routers. That makes sense. It's a router solicitation. 16 is reserved for multicast listener, and now we know what this multicast solicited address is. All right, just like IPv4 has some special addresses like all zeros, IPv6 has the same thing. Unspecified IPv6 address is just : right? That's the equivalent of IPv4 0.0.0.0. Loopback is : 1, which is equivalent to 127.0.0.1. And then I said I would talk a little bit about anycasting. Anycasting is a thing that we have with IPv4. We also have with IPv6. If you have an address that needs to be reached by a whole bunch of different nodes, and the nodes are spread all over the place, one of the optimizations that we have is that we can have a whole bunch of routers understand that particular IP address. And so this IP address is not a single destination, it is reachable by multiple routers. And routers will forward the traffic to the nearest router or server that supports that particular service. So the same IP address might be reachable or may terminate at different locations all over the place. So that is anycasting. It's quite handy when you're dealing with things like content delivery services or streaming. And the way that you would specify that is with that last argument that we saw when we were looking at our IPv6 addressing. We just specify that it's anycast. But this also means that that address would appear many, many other places, and that routers would have to know how to route to that address. Did you or did I know this already? Questions? Question number one, router 1 has an interface, G01, with a MAC address. Which of the following commands added to the configuration would give the interface a unicast IPv6 address of, what do you see there? And the answer is just the first static configuration mode that we had, right? So you just specify IPv6 address and then what you want it to be. So standard format. Question number two, router 1 has an interface named G01 whose MAC address has been set. The interface has been configured with an IPv6 address with the EUI argument, the EUI64 subcommand. What unicast address will the interface use? Well, this is your understanding of the conversion, right? So we just stick FFFE right in the middle, and then we flip that bit on the 7th bit. So it's 52, 55, 44, and so on. Router number 1 currently supports IPv4, routing packets in and out of its interfaces. Router 1's configuration must be migrated to support dual stack for both. Which of the following tasks must be performed before the router can support IPv6? Well, we know the answer to that one. We've got to turn on IPv6 unicast routing and then give the interfaces their IP addresses. Question number 4, on a router configured with an IPv6 address, which commands will show the prefix? Choose two. Well, B and D show IPv6 interface brief or just showing the interface itself. And we saw that prefix length in the examples earlier. Question number 5, router 1 has an interface, G01, with the MAC address configured. The interface is then given an IPv6 address. If no other interface commands are used, which of the following will be the link local used on the interface? Well, again, the conversion, but in this case, it's got the MAC address configured, right? So you'd be putting it in there, flipping the bit, and then doing all the zero suppression. So that was A. Question number 6, which of the following multicast addresses is defined as the address for sending packets to only IPv6 routers on the local link? Well, we know that was the all routers multicast, so FF02::2. And the important thing there is the ::2 is the all routers, and the first two, FF02, that's the scope. Question number 7, host C must forward a packet to its default gateway. And there's our default gateway address. Host C does not yet have a neighbor table entry for that address. To which solicited node multicast will the host C send its NDP neighbor solicitation? Well, we know now that the solicited node multicast will have FF, right? It'll have this pattern here, FF02::1 FF, followed by that node's unique identifier. Now, question 8 is a little tricky. It has a whole bunch of IPv6 commands that all worked, and you have a couple of interfaces that we're dealing with here, 01, 02, 03. What happens after all this is done? The answers were B and C, that G001 would have a link local address, but no other addressing, and G002 would have the identical configuration. All right, the Chapter 28 look ahead, as promised. What are we going to do about not having broadcast addresses? So we have to do the neighbor discovery. We'll talk a little bit more about multicasts and how we deal with hosts and routers. And as part of that neighbor discovery process, we're going to deal with solicitations and advertisements. Two different kinds of messages, right? One is you're looking for somebody, and one is an actual advertisement. And we'll do a little bit on the dynamic side of addressing. Well, hey, how about those IPv6 addresses? So this time we knew coming in about global unicast and unique local addressing, but we've added now link local, anycast, unspecified, and dynamic versus static addressing discussion. We also know a lot more about multicasting than we did before. So like and subscribe if you're ready for that neighbor discovery process, ready to understand what you do without broadcasting. And no matter how you're finding those nodes, may those packets always reach their destinations. And remember that we're working through IPv6 and the CCNA. You can do this.